Hello, everybody, and welcome to another wonderful day of chemistry. So last time we were talking about various physical and chemical properties. Well, one of the unfortunate features is when we're making use of physical properties, we have to go ahead and do so by making use of scientific units. So the classic English standard uh, units such as pounds and feet just won't work for science because we use SI units. So anybody who wasn't educated in America, here's an advantage for you. So we're going to be talking about six major properties of units: length, volume, mass, time, temperature, and density. However, there are many more units out there that could be of relevance, such as electric potential and velocity and acceleration, but these are going to be the ones that are most useful for describing chemical systems. However, in order to do so, we need some standard units of measure. So again, as I said, we're going to go ahead and make use of the SI units. So the big ones that we're going to be dealing with are meters, kilograms, seconds, Kelvin for temperature, and we're going to get to this one later, but amounts of substances are often measured in moles, but we also are going to have a fair number of, we can also combine some of these units to give us units of volume, which can either be done in cubic meters or liters, and density, which is a combination of mass and volume. So one of the biggest advantages of SI units over English standard is when we're scaling them either up or down, because most of our systems aren't going to be measured in the base unit. And in SI and English standard, it's say hard to go from pounds to ounces. So to keep it simple, we work in a base 10 system in SI. So most of you are familiar with this. We're going to be working with a couple of key ones most frequently. We're going to tend to work by the powers of 3 most often. So going up, we go to kilo, mega, giga, and tera. Now, one of the cool features here is you'll notice that these tend to go by powers of 3. So one of the other useful things that I find is counting these on your hand. So your first finger is for thousands, millions, billions, trillions. So a kilo is 1,000 of the base unit, mega is 1 million, giga is 1 billion, and tera is 1 trillion. Works fairly easily when you work it that way. Feel free to count it on your fingers. Also, this can be very useful if you think about computer memory. Byte, kilobyte, megabyte, gigabyte, terabyte. A terabyte is 1,000 gigabytes. A gigabyte is 1,000 megabytes. A megabyte is 1,000 kilobytes. And a kilobyte is 1,000 bytes. So that's a good way when you're working up. Now, when we're working down, it is worth noting that we do make fairly common use of centa, and occasionally we'll use deci. So deci is going to be 1/10. This is actually the origin of decimate, where you remove 1/10 of a population. We also have centa, most commonly known as in a centimeter. There's 100 centimeters in a meter. However, the big ones that we're going to be using fairly frequently are going to be milli, micro, nano, pico, and femto. We're going to be using these lower ones a little less frequently, but it's still good to know them. These follow the same basic patterns. Go by orders of 3, starting with milli, 1,000, 1 million, 1 billion, 1 trillion, 1 quadrillion as you work your way down. So there's 1,000 millimeters in a meter. There's 1 million micrometers in a meter. There's 1 billion nanometers in a meter, and 1 trillion picometers in a meter. So it works fairly nice that way. And again, feel free to count on your fingers: 1,000, million, billion, trillion. 1,000, million, billion, trillion, quadrillion. So fairly useful there. Though watch out for the classic prefactors. So if I'm representing a centimeter, it would be cm. If I'm representing a centigram, it'd be cg. Same thing with a milligram and a millimeter, mg and mm. And again, micro, nano, pico, femto, or going up K, M, G, and T. So these are actually a very nice modification when working through our units. Now let's go ahead and get an idea of what some of the more common units are, because I find that knowing my SI units is most helpful if I can put it in a common reference. So first one we're going to be talking about is mass. It's a measure of exactly how much stuff a substance is, or how much is there. And here's one of the nice things that we see for mass instead of weight is that it stays the same no matter where the measurement occurs. It is indeed just a measure of how much substance is there. So if I'm looking at a kilogram, this is about the same as 2.2 pounds. I often approximate it as about 2 pounds. Most usefully is 1 kilogram is a liter of most liquids. So if you have a liter of soda, that's a kilogram. If you have a 2-liter bottle, that's about 2 kilograms, or about 4.5 pounds. So that's actually a fairly useful way to think about it. Liters of soda when you're talking kilograms. When you're talking about grams, this is actually a fairly small unit. It's 1/29th of an ounce. Hard to internalize there, but it's about the weight of a dollar bill. So a gram really doesn't weigh that much. Interestingly enough, this also tells us that $1,000 bills weighs about the same as a liter of soda. Kind of interesting when you see the movies, people moving around bags full of cash. All right, a milligram is actually really light. It's approximately the weight of a grain of sand. When you get below there to micro or nano, this is actually really too small to kind of internalize. Now, one of the important difference is the difference in between weight and mass, because weight's going to be the force exerted by a substance due to gravity. So it's how much a given mass will push down a scale. That's really what weight is. And it's an important difference in between weight and mass. Because one of the cool things is that weight depends on where a measurement occurs. If you are further away from a source of gravity, you're going to weigh less. And actually, a kind of a cool thing is if you weigh about 150 pounds at sea level, you're going to weigh 149.9 pounds on Mount Everest. So it is worth noting that over kind of Earth scales, there isn't too much difference. But by using mass, we're also able to take chemistry and apply it to things like how chemistry or astrochemistry, or how chemical reactions occur in space. So it's a much more consistent unit of measure and fairly useful in that way. Another important one is going to be temperature. So here in the US, we make use of Fahrenheit. However, a more useful one is going to be either Celsius or Kelvin. We can make use of both, but in general, when in doubt, go for Kelvin, and I'll illustrate why in a bit. However, in order to convert in between Fahrenheit and these, it's often easiest if you first go to Celsius. So you can determine the temperature in Celsius by subtracting 32 and then multiplying by 5/9. So, for example, if I have a 32-degree day, that's freezing temp, which lo and behold gives me a 0 degrees Celsius. This is kind of the defining feature of Celsius, is it's zero at the freezing point of water. However, we can also go from Celsius to Fahrenheit. To do this, we reverse the process. We multiply the temperature in Celsius by 9/5 and add 32. This means that I can go ahead and go to the boiling point of water, which is about 100 degrees C, do the conversion, and it turns out to be about 212 degrees Fahrenheit. So some interesting features along the way is, so a hot day is about 30 degrees Celsius or 86 degrees Fahrenheit. And there is a very magical point at -40 where Celsius and Fahrenheit are the same thing. Also, another useful point is 50 degrees C is about the point at which you can start cooking meat. And this turns out to be about 125, 130 degrees Fahrenheit, which is actually interesting because with global warming and in certain cities, we're starting to reach that temperature, which means that it is actually possible to cook yourself out in the middle of a hot city on a hot day. Gotta love global warming. However, when doing mathematical relationships, it's often really useful instead of using Celsius or Fahrenheit to make use of Kelvin, because Kelvin is an absolute scale. So there's no negative values, can never quite get down to a temperature of 0 degrees Kelvin. And it's actually a very nice conversion in between Celsius and Kelvin. To get to Kelvin, you'll simply take your temperature in Celsius and add 273.15. However, this also means that negative 273.15, you do reach 0 Kelvin or absolute zero. So we never quite get to this point, but we get pretty close. Now, I do want to emphasize one of the reasons why Kelvin is very useful is if you ever find yourself multiplying something by temperature, well, weird things happen if you use Celsius or Fahrenheit because it's possible to have a 0 temperature for those, which yields to some very weird equations. So in general, when in doubt, use Kelvin for mathematics. However, it is from day-to-day use much easier to use Celsius. So we'll be mostly moving in between Celsius and Kelvin. For now, forget Fahrenheit exists. Now, another one of our classic favorites is distance or length. So when measuring length, we're going to make use of the meter. So thankfully, we actually have a pretty analogous unit in English Standard. It's about a yard. Good way to think about this is for a typical person, this is about waist height. Does depend on your size though. 1 centimeter is about a little less than half an inch. The metric that I often use to estimate a centimeter is it's about the width of a finger. If you've got bigger hands, use your little finger. If you got smaller hands, you can probably use one of your main ones. But when estimating lengths, this is actually a fairly good use. Now, a millimeter, this is about the thickness of a credit card. So this is going to be a pretty small unit. But when dealing with small things, as we're often doing, we'll be using it a fair bit. Now, one of the things to watch out for is when we're making use of volumes, because volume is essentially a cubic, is often represented as cubic volumes. This is the same as a distance raised to the third power, which can do some odd things when doing unit conversions. So if I'm wanting to go from, say, a cubic meter to a cubic centimeter, what we have to do is remember that I'm raising everything inside my conversion to that third power. So 1 meter cubed is the same thing as 10 centimeters cubed. So I have to cube both the 10 and the centimeters. So 1 cubic meter is about the same as 1,000 cubic centimeters. So this can lead to some difficulty when making use of conversions. However, it is also worth noting that cubic volumes can also be converted to SI units of volume. The one that I typically like to make use of is 1 milliliter is the same as 1 cubic centimeter is the same as 1 cc. So if you ever hear in one of those medical dramas people yelling out, I need 10 cc's of whatever stat, they're just asking for 10 milliliters of something. It's a little pretentious of a unit. It's just a milliliter. However, another common one that is used is 1 liter is the same as 1 decimeter cubed. This is a little bit odd. We typically don't make use of decimeters, but a good way to think about this is 1 liter is the same thing as 1,000 cubic centimeters. So, making use of our volume and masses, we can now move on to density. So we can combine our mass and volume to get a ratio of density. Now, one of the useful features of density is it's what's called a size intensive property. So if I have a size extensive property, this means that I depend upon how much of a substance I have. However, density is a size-intensive property. It doesn't matter how much of a substance I have, it will always have the same density, whereas the amount of substance I have will change mass and volume. So if I ever take the ratio of two size-intensive properties, or two size-extensive properties, I get one size-intensive property. And this is a fairly useful feature. So a good thing to keep an eye out for densities is for solids, we typically have densities in between about 0.2 grams per centimeter, which is often things that are very not very dense, such as gels. So think about a jello. It doesn't weigh a lot for its size, all the way up to 20 grams per centimeter. And so this is for one of the heavier natural occurring elements of osmium. Liquid densities tend to be a little bit more confined in between about 0.5 grams per milliliter and 4 grams. You often get these higher densities on the lower range because you don't include air, such as in most of the gels. But in this lower range, you typically heavy elements tend to space out when they go into a liquid phase. One of the good standards is water. So water has a density of about 1 gram per milliliter. This is also going to be the same thing as 1 gram per centimeter cubed, or 1 kilogram per liter. So these are fairly useful conversions when dealing with aqueous or water containing systems. However, gas densities are typically very light, so we make use of we are typically measuring these on the orders of grams per liter. Also, an important feature to make note of, solids typically have densities reported in grams per centimeter. Liquids and gases tend to use grams per milliliter or volume. Also, when when trying to internalize densities, if I have two substances of equal volume, the more dense object is going to be the heavier object, the one with a larger mass. However, if I've got two items of equal mass, the more dense object is going to have a smaller volume. So it's going to be the smaller object if it's more dense. If I have two masses, the more dense object will tend to be smaller, even though it's the same weight. So with all of our various units in mind, next time we're going to be talking about one of the first things we need to do in order to conduct mathematical conversions, which is to understand significant units. Until then, take care.